Now let's do a slightly more complicated example about Ampere's circuital law. So what we're asked to do is we are given a tightly wound coil of wire. And here's my coordinate system that I'm going to use. The z-axis goes down the middle of the coil. Actually, the z equals 0 plane is right here. So we've got z, that's x, that's y. We're not going to use them. A current is circulating around the coil like this. So it's flowing in the phi direction. And the coil extends from minus L over 2 to L over 2. So L is the length of the coil, and it's got some radius that is, do we care about the radius? We don't care about the radius for now, but we can give it a radius. We can call its radius A. All right, so we have a tightly wound coil, and we want to find the magnetic field in the middle of the coil, like down the center. And we are assuming that the length of the coil is much greater than its radius. All right, let's start by examining the symmetry. The reason that we know that the length is much greater than the radius, and that the reason that this is relevant, is because at any point inside the coil, the fact that the length is much greater than the radius lets us basically assume that you can't see the ends from the point at which we're trying to measure the magnetic field. So the coil looks essentially infinitely long over the region that we care about. Or at least we can pretend that it does. Next, what direction is the magnetic field going to flow in? At this midpoint, IDL is always going to be phi directed. And let's say I choose a point over here. It's always going to have, the A hat R is always going to have components that are in minus A hat rho and plus or minus A hat Z directions. All right? So A hat R has minus A hat rho and plus or minus A hat Z components. What that means is that when we do IDL cross A hat R, remember IDL is phi directed, we're always going to end up with A hat phi cross minus A hat rho, which will get us A hat Z. But when we cross A hat phi with this plus or minus A hat Z thing, which depends on whether our IDL element is below or above the observation point, we're going to have either a minus A hat rho or a plus A hat rho. And as we have made this symmetry argument multiple times before, for any IDL that we choose on the bottom half of the cylinder that produces a hat R component that has a positive Z direction, we can choose one on the other side that will cancel it by having a negative Z component. So we're only going to have this A hat rho component. Sorry, we're only going to have this A hat Z component because we can cancel all of the things that result in A hat rho components. So A hat phi cross plus or minus a hat z equals plus or minus a hat rho, and these cancel because we have both positive and negative components. So H is z-directed. That's what we learned from all of that. And since it is infinitely long-ish, H is uniform along the length of the cylinder. We're engineers so that we can make assumptions like this. And again, this is because we can't see the ends of the cylinder from a point inside the cylinder. So that's the first step. We have decided that H has constant magnitude and it's z-directed. Cool. The second step is that we need to define our Amperion loop. How are we going to do that? We're going to erase some things to make some room on my drawing. There we go. Looking good. So if you remember, our requirements for the loop are that H has to be parallel or perpendicular to DL, or you can have H equals 0 everywhere. And we need to be able to compute how much current is flowing through the loop. Computing how much current is flowing through the loop is pretty easy. We are given that this is a coil with n turns. So that means it has n loops and it is carrying current I. So the current flowing through this thing is just going to be n times I. That's easy. But what about this? Here's how you do it. You define your Amperion path to go down the middle of the coil, horizontally out. You let it go all the way to infinity, and then vertically back. So here's what happens. On the top and the bottom edges, H is perpendicular to DL. On the edge that is at infinity, H goes to 0. And then here down the middle of the coil, on the inside, H is uniform and parallel to DL. So our Amperion path is this rectangle that has one side that goes up the middle of the coil along the direction that we expect H to be going. And if you remember, we need to define the surface normal of the surface that is traced out by this path, or that this path is the boundary of, to agree with the direction of the path itself. So the path, I'm going to assign the surface normal to agree with the direction that the current is flowing. So the surface normal is into the board, which means by the right-hand rule that my path has to go clockwise the way we're looking at it. So that's step 2. We have defined a path. Step 3 is we need to actually integrate around the path. on three sides of the path, our integral is going to work out to be 0 because h dot dl is 0 on the top and the bottom. H itself is 0 at infinity, so we only really care about this leg. So our closed loop integral of h around the path turns out to just be integral from minus L over 2 to L over 2 of h, which I'm going to write as h a hat z because we know its direction. So our variable here that we need to determine is just h, is equal to the current flowing through this surface, which, as I just explained, is n, the number of loops in the coil, times the current that is being carried by the loops. Carrying out, ooh, I forgot a dz there. Completely left out dl. What am I even doing? Okay, anyway, you evaluate this dot product, it evaluates to 1, so then we end up with HL equals NI, or H equals A hat Z, NI over L, the length of the coil.